Hello everyone, welcome to my lovely apartment. Don't worry, that column in the basement was fixed, so I'm pretty sure the floor is not going to collapse. Uh, so last week we talked a bit about axial forces, and we're going to start with a little review. So as you can recall, axial forces are when we apply a force along the axis of a member. In other words, I'm going to pull up on this member and I'm going to apply a reaction down here in line with the force that I'm applying. And if I pull, I create tension. If I push, I create compression. And just so you can take a look at this a little more closely, when I pull, the lines spread apart. When I push, they start to come together, but then of course we have another mode of failure with compression, and that is buckling. And you can see that the buckling is occurring along the weaker dimension, the shorter dimension of this foam column. Of course, I can change the capacity of this column by either supplying a different end condition. So in this case, we would be pinning both top and bottom, and we would have a length of L, and K would be equal to 1. But I can also fix the top of this column against rotation by clamping down on it with my hand. And now you can see that the buckling shape is a bit different, and I'm able to apply a little more force before it starts to buckle. I can also change the buckling length of this column and increase the capacity by applying some bracing. And all I'm going to do here is just very lightly place my fingers on either side, and you can see that once again the buckling shape has changed. And in this case, we now have essentially cut the length of the column, the buckling length, in half. And by doing that, we have increased the capacity of this column by 4 times. And that's of course because in Euler's buckling formula, the KL is squared. So you can see that this foam is very flexible. In other words, I can apply very little load or stress and immediately get a noticeable amount of change in its length or strain. So in other words, this foam has a very low modulus of elasticity. And that's going to be very useful for this demonstration because often terms like stress, strain, modulus of elasticity can be a little difficult to understand. But if we can take a look at the deformation of this member under loading, hopefully those terms will start to click. So now that we've reviewed axial forces, this week we're going to take a look at perpendicular forces. And so I'm going to take this member, turn it on its side, and apply 2 reactions at either end, 2 support reactions. Then I'm going to take a weight or a force and apply it somewhere perpendicular to the length of this member, a certain distance away from my support reactions. And as we learned last week, force times a distance is going to create twisting or moment about the axis coming this way of the member. So if you take a look at the ends of this member, you can see this rotation occurring. And that rotation is happening about an axis that's coming out in this direction. Or in other words, if I were to take this member and grip it just in my hands and try to apply that same type of shape to the member, I would have to twist my hands around my thumbs like this. You can see I create that same shape with the member. So when we apply a force to a member a distance away from the support, we create bending. And of course, the location of this weight changes the amount of bending that's applied. So if I place this at midspan, that's where we get our maximum amount of bending. However, if I move it closer to the support, you can see we get much less bending. And again, that's because bending is equal to force times distance. So decrease the distance, decrease the bending moment. But it's important to note that we are not only creating bending in this member, we are also creating shear. And shear is best understood by looking at a pair of scissors. Scissors work by taking two knives and placing them slightly offset from each other, but very, very close together. And you can imagine that if I were to place my piece of foam between these two scissors and clamp down, this piece of foam would fail very easily in shear. It would cut in half. But let's focus on bending for a moment. If I rotate this piece of foam to show you these lines again, I'm going to come a little bit closer. And then if I apply that same rotation at either end to create bending in the member, you can see that the lines that I've drawn at the top, they become closer together. At the bottom, they spread further apart. And so we're creating compression at the top and tension at the bottom. Or if I change my rotation, now I'm creating tension at the top, compression at the bottom. There's also this line that I've drawn in the middle here, and this is called the elastic neutral axis. And that is where our bending stress is going to be zero. There's no change occurring in the member along that elastic neutral axis. And so if I were to plot the amount of stress in the cross-section of this member as I'm applying bending, it would look like this, where we have maximum tension at one side, maximum compression at the other side, and zero stress at the neutral axis. We're looking at the piece of foam. If I were to cut this somewhere as I'm bending it and take a look inside the member, we would see maximum tension up here, maximum compression down here, and no stress in the middle. Now also know what happens when I apply too much bending to this member. You can see at a certain point it pops and twists. So if I turn it on the side here, well, you can see that it pops. And this popping we call lateral torsional buckling. Lateral, of course, means that it's happening out of plane of the member. Torsional is what we call twisting. And buckling, as we learned before, is how members fail in compression. And as we just learned, when we apply bending, we're also creating compression. And therefore, we have the potential for buckling.